Okay, welcome to Symbolic Logic Unit 5. Last time, we looked at the way in which atomic sentences compose more complex sentences, not in a very formalized way, but sort of in an informal way. So today, we're going to look at the way in which the connectives function. So we're going to be investigating how to make complex sentences out of these simple sentences we looked at last time, out of the simple atomic sentences. And to do that, we're going to use what are called connectives. So connectives are essentially these kinds of logical operators or logical functions that allow us to generate longer true-false sentences from atomic and other shorter sentences. Okay, so we're going to be learning about the connectives today. There are 5 of them we're going to be learning about. So again, these atomic sentences are the simple possible sentences that can be true or false. So as an example, consider the sentence, Charles runs. And note that if we subtract Charles or runs from this sentence, we no longer have a statement that can be true or false, right? Consider Charles. Charles can't be true. We can't say it's true that Charles, or consider runs. We can't say it is true that runs or it's false that runs. So it takes these 2 parts to make something that's capable of being true or false. The basic thought here is that an atomic sentence consists of a single verb and however many objects that verb takes. So in the case of an intransitive verb, such as runs, you just need the subject for that verb. So you can have Charles runs, the subject and the verb. In the case of a transitive verb like hits, you would need subject and direct objects. So Charles hits the ball, for example. But the basic idea is atomic sentences have one verb and however many objects that verb takes. So again, atomic sentences are going to be represented in sentential logic using capital letters. So we'll use C to stand for the sentence Charles runs, for example. Okay. So how do we build complex sentences? Well, if atomic sentences are the basic building blocks of our more complex sentences in sentential logic, then the more complex sentences are going to be constructed using these sentences, either atomic sentences or in some cases more complex sentences, and connectives. And again, there are 5 connectives that we're going to be learning about in sentential logic. So for each connective, there's going to be a space or a gap where you can put a sentence. And the outcome is going to be a more complex sentence that's capable of being true or false. So for each of the connectives that we're going to look at, negation, conjunction, disjunction, conditional, and biconditional, I've identified where the sentences you would conjoin to these connectives will go to generate the more complex sentence. So notice, the red spaces are going to be where those other sentence parts go to form the new sentence. And notice that negation is the only connective that has only one space or gap. The rest of them have 2. So we can throw a negation in front of any sentence to generate a negated version of that sentence. But for the others, we have to have 2 sentences that are going to be joined together using the connective. So here we have, it's not the case that C, right, which would mean it's not the case that Charles runs or Charles doesn't run. Suppose A stands for Amy runs. Then for the conjunctive sentence, we would have Charles runs and Amy runs. Suppose, and for our disjunctive sentence, which is the sentence below this, we would have Amy runs or Charles runs. This sentence is a conditional. And a conditional is essentially an if-then statement. So for this, we would have, if Charles runs, then Amy runs. And then finally, for our biconditional, we would have Charles runs if and only if Amy runs. So those are our 5 connectives that we're going to learn about in our first section on sentential logic. Again, they are negation, it's not the case that, conjunction, which we might paraphrase in English as and, disjunction, which we can paraphrase as or, the conditional, which equals an if-then statement, and the biconditional, which is if and only if. Okay? So we're going to talk about these in more detail today. So first, what I want you to try to do is to translate each of the following from SL into English. Oh, actually, I've already given you the translations to these, so we're going to kind of skip over that. So we have, it's not the case that Charles runs again, Charles and Amy runs, Amy or Charles runs. If Charles runs, then Amy runs, and Charles runs if and only if Amy runs. All right, let's dip in a little more closely to the negation connective. So consider this sentence: logic is hard. Well, we might represent each of the following three sentences using the negation H sentence. So we can say, it is false that logic is hard using negation H. We can say, logic isn't hard using negation H. We can say, it is not the case that logic is hard using negation H. All three of those are equivalent from the point of view of symbolic logic. So there are going to be instances where an English language sentence, even though two English language sentences don't look like they're the same, they actually have the same representation within sentential logic. Again, what we're interested in sentential logic is truth functional equivalence. And so each of these sentences are true under all of the same instances. So we can symbolize them all using not H. All right. So for any sentence, and I'm going to use this variable phi. So this is a Greek letter. For it, this letter is going to stand for, phi and other Greek letters are going to stand in for variables for sentence letters. Okay? And so essentially the thought here is phi is standing for any possible sentence you might plug in there. H, has a specific meaning. Logic is hard. But phi can stand for any sentence whatsoever. So for any sentence phi as it's not the case that phi, if it can be paraphrased in English as it is not the case that phi, right? So again, we can symbolize anything as negation phi so long as it's possible to paraphrase it in English as it is not the case that phi. And of course, it is false that logic is hard can be paraphrased as it is not the case that logic is hard. So we can use that negation symbol with negation H, just as we can for logic isn't hard or for it is not the case that logic is hard. So note here that connectives don't merely make more complex sentences. Of course, they, together with sentence letters, are the basic building blocks for complex sentences. They do serve to make more complex sentences, but that's not all they do. They're significant because the truth or falsity of the complex sentence depends on the truth or falsity of the input sentences and the connectives. In other words, the truth value of the complex sentence is determined functionally from the truth value of the sentences together with the operations that the connectives perform. So in philosophy, we'll say that the connectives are truth functional connectives because they can be seen as a function that moves us from the truth value of whatever the sentence was before they were added to the new truth value once they've been added to generate a more complex sentence. Negation always produces a false sentence if the input sentence is true, and it always produces a true sentence if the input sentence is false. So here's our rule for negation. If phi is true, then it's not the case that phi is false. And if phi is false, then it's not the case that phi is true. So here's a second note. And you can put any sentence of SL in the gaps of a connective to form a new sentence. And so this applies to atomic sentences, as we've been thinking with logic is hard or Charles runs, but it also applies to more complex sentences. You can put a complex sentence in a connective as well. So consider this sentence. It's not the case that Charles runs. Well, we can attach a negation to that complex sentence to generate it's not the case that Charles runs. Or more simply in English, Charles runs. That would be the meaning of this sentence. Similarly, we can attach a negation to the front of this thing, which is represented here in red, to get it's not the case that Charles runs, which is just equivalent to Charles doesn't run. And then you can also do this not only using the negation symbol, but also connectives such as and or. So this sentence, the last one, means it's not the case that A and C. It's not the case that both Amy runs and Charles runs. In other words, at least one of them doesn't run. So this is important to note. We can add connectives to atomic sentences, but we can also add them to more complex sentences to generate new sentences. All right, so now I want you to watch as Michael Scott from The Office performs this in ordinary English. So he's going to negate a negation in this little. So now I want you to translate the following into English in the same way that Michael Scott did in this clip, right? So essentially we have, it's not the case that, it's not the case that, it's not the case that Charles runs. And so that will be equivalent to, it's not that Charles runs. So let's turn to conjunction now. Consider the following sentence. J, Jessica is strong. And here's another sentence. L, Luke is strong. So we have J and L equaling Jessica is strong and Luke is strong. So each of these sentences, J and L, are called conjuncts when they are part of a sentence connected with our conjunction symbol. So if we have a conjunctive sentence, J and L, then each of the things conjoined by the conjunction symbol are called conjuncts in that sentence. So that's a term of art that I'll be using moving forward. So here's some more examples of conjunctions. Jessica is strong and grumpy. Jessica and Matt are both strong. Although Luke is strong, he is not grumpy. And Matt is strong, but Jessica is stronger than Matt. All right, let's look at how to translate these using symbolic logic. We can bear in mind here that and can stand in for both and, both, but, and although. All right, so let's turn to the iPad to see how these function. So let's translate these examples of conjunction. So we have here a key up at the top, and now we're going to consider this key in translating these. So what we'll say is, Jessica is strong. A stands for Jessica is strong. B stands for Jessica is grumpy. C stands for Matt is strong. D stands for Luke is strong. And E stands for Luke is grumpy. And F finally stands for Jessica is stronger than Matt. For now, we have to symbolize this sentence using a single sentence letter. But later on in the course, we move on to quantified logic or predicate logic. We'll be able to symbolize this sentence in a more intuitive way that reflects the underlying structure. But for now, if we want to translate these sentences, 12 would be A and B. 13 would be, so 13 is Jessica and Matt are both strong. So for this one, we need Jessica is strong and C, Matt is strong. 14 would be, so we have although Luke is strong, he is not grumpy. Now, as we just saw, and as is reiterated here, although can be paraphrased as and. So we would understand this as and Luke is strong, he is not grumpy. Or if we wanted to flip the order of those two clauses, we could get the more intuitive. It is not the case that Luke is grumpy and D, Luke is strong. Okay, it is not the case that Luke is grumpy and D, Luke is strong. Later on, we'll learn about parentheses, and this would mean something very different. This would mean is not the case that Luke is both strong and grumpy. But that's not what we're dealing with here. This just says it's not the case that Luke is grumpy and Luke is strong. Okay, and then finally, our final sentence, Matt is strong, but Jessica is stronger than Luke, would be C, Matt is strong, and we can understand but as and, we know. So, and Jessica is stronger than Matt. And so this is going to be how we translate these four sentences. Okay, let's return to the PowerPoint now. Sentences that can be paraphrased phi but psi, or although phi, psi, or phi and psi are best symbolized using a conjunction. So using the symbol phi and psi. Okay, and again, we're using these Greek letters to stand for any sentence, right? So essentially, any sentence variable could be plugged in here, any simple sentence, any complex sentence. What we're saying is all of these sentences, it could be translated as phi but psi, or although phi, psi, or phi and psi are all going to be best symbolized using a conjunction. So let's continue. For each connective, the truth or falsity of the complex sentence depends on the truth or falsity of the component sentences. So here is how this works for conjuncts. So if we have phi is true and psi is true, then we're going to get a sentence that is true. In other words, if it is true that Jessica is strong, and it is also true that Jessica is grumpy, then the sentence generated by combining those two things will be true. The sentence Jessica is strong and grumpy will be true if the underlying sentence Jessica is strong is true, and the underlying sentence Jessica is grumpy is true. Another example, or to go on rather, if one of our sentences is false, then the conjunct will be false, right? So if Jessica is not grumpy, then the sentence Jessica is strong and grumpy is going to be false. And likewise, if Jessica is grumpy but not strong, then the sentence Jessica is strong and grumpy will also be false. So any one false conjunct renders the complicated conjunction false as well. And of course, if both of our conjuncts are false, then the sentence is also, the conjunctive sentence generated using those two conjuncts will also be false. Let's look at disjunction now. Again, we're going to use a kind of example here. So Jessica is strong and Luke is strong. We use those again. So we could represent, we could write the following using these simple sentences. J disjunction L. And this would mean Jessica is strong or Luke is strong. So each of the sentences J and L in this complex sentence are called disjuncts when they're part of a sentence connected with our disjunction symbol, or, in English language. And just as a connective, disjunction says that at least one of the two of its disjuncts are true, right? So if we have the sentence, Jessica is strong or Luke is strong, that sentence will be true as long as one or the other is strong, as long as Jessica is strong or Luke is strong. It doesn't require that both be strong, though if Jessica is strong and Luke is strong, then it's also true that Jessica is strong or Luke is strong. So we'll talk about this more a little bit later. But basically the idea is that this is known as inclusive or. Right? So you might think, for example, that or means one or the other, right? So if you walk into a restaurant and there's a meal deal that includes, let's say, a sandwich and soup or a salad. Presumably, you would interpret that as saying you get one or the other. You get soup or salad. But in fact, that's a kind of implication of the situation that you're in. Or doesn't always have to mean one or the other. It can also mean both. So imagine that the waiter said, "Would you like soup or salad?" And you start to choose one, and he's like, "Oh, you can have both if you want." That wouldn't violate the truth of the statement that you get soup or salad. Another example, suppose that you want to know if a bill withdrawn from your banking account will have led to you overdrawing your bank account. You think, I will be safe in this case if the bill that I have to pay wasn't automatically withdrawn, or if my paycheck came through, right? Now, suppose that your paycheck came through and the bill you have to pay wasn't withdrawn. Then you're still not going to be overdrawn. So an or statement doesn't require that only one of the things be true. It can be the case that both of them are true, and still the or statement will follow in that case. So again, as a connective, disjunction says that at least one of the two of its disjuncts are true, and it may be that both of them are true in order to render the thing true. So consider the following example. Dennison will golf with me. Ellery will golf with me. So we have the sentence D or E. Either Dennison will golf with me or Ellery will golf with me. Either Dennison or Ellery will golf with me. Both of these can be symbolized in the same way using this disjunction. A sentence can be symbolized as phi or psi if it can be paraphrased in English as either phi or psi. And both of these can be paraphrased in that way. So both of these can be translated to D or E. However, each of the disjuncts must be a sentence in its own right. It must be capable of being true or false. So for each connective, the truth of the complex sentence depends on the truth or falsity of the component sentences. And here's how it works for disjunctions. So if we have a disjunction phi or psi, and phi is true and psi is true, then our disjunction is true. If phi is true and psi is false, then our disjunction is still true. If phi is false and psi is true, then our disjunction is still true. The only time a disjunction is false is when both of its disjuncts are false. Okay, now let's turn to a practice exercise. So as this practice exercise, I want you to translate using the three connectives that we've already covered. And these again are negation, disjunction, and conjunction. So here are our sample sentences here. S1 stands for you will get soup. S2 stands for you will get salad. And so first, let's try to translate this first sentence into English. So this is open parentheses, S1, or open parentheses, S1 and S2, close parentheses, close parentheses. So you can translate, as a tip, I want you to translate inside of the parentheses first, okay? So we're going to translate from the deepest set of parentheses, which is this set, S1 and S2. And now when we translate that, we get S1 or you will get soup and you will get salad. So now we have to translate S1 and we'll end up with you will get soup or you will get soup and you will get salad. And we could simplify this by saying you will get soup or you will get soup and salad, all right, which sounds a little bit more obvious in English. So let's translate each of these following sentences. So take a stab at this. Okay, and here these are. Let's try them. So if we have not S1 or not S2, what will that get translated to? Well, it gets translated to it is not the case that you will get soup, or it is not the case that you will get salad. Or to put it more colloquially, we might say, you won't get soup, or you won't get salad. So that's the first one. For our second one, we would translate this as it is not the case. So notice the not is on the outside of the parentheses there. That you will get soup or salad. Okay. We might say you won't get either soup or salad in that case. And then our third option is going to be as follows. it's going to say, you will get soup or salad, and it's not the case that you'll get soup and salad, or it's not the case that you'll get both soup and salad. And so this is what we could call the exclusive OR. This is the OR that's in place when you go to a restaurant and they say you get one or the other, but not both. Okay, let's go back to the PowerPoint. Okay, so there's a look at complex sentences that use both and, negation, and or. So let's move ahead to look at some other of our connectives. So a very important connective in symbolic logic is the conditional symbol, which we're going to symbolize with this horseshoe, sideways horseshoe. So consider the following sentences again. Jessica is strong and Luke is strong. So how would we interpret Jessica conditional L? Well, the way in which we would interpret that is essentially as the horseshoe providing us with an if-then. The if gets interpolated in front of the J sentence, Jessica is strong, and the then gets interpolated between the two sentences before L. So here's that sentence. If Jessica is strong, then Luke is strong. So when we talk about conditional sentences, we're going to refer to the if clause sentence, Jessica is strong, as the antecedent. And we'll refer to the then clause sentence, Luke is strong, as the consequent. So in other words, the antecedent is what comes before the horseshoe, before the conditional symbol, and the consequent is what comes after. And essentially what this is saying is that in any situation where that antecedent is true, then the conditional has to follow. But this isn't telling us that the antecedent has to be true if the conditional is. It has a certain directionality to it. So a sentence can be symbolized as psi, if, then, phi. And remember, we're using these to stand in for sentence letters and that we might use when we're constructing or when we're translating a sentence. So a sentence can be symbolized as if, phi, then psi, if it can be paraphrased in English as if, phi, then psi. And the antecedent and the consequent must each themselves be a sentence. So for each connective, the truth of the complex sentences, again, depends on the truth or falsity of the component sentences. And so here is how that works for conditionals. So for a conditional, if the antecedent is true and the conditional is true, then the conditional statement is true. Also, for a conditional, if the antecedent is true and the conditional is false, then, if the antecedent is true and the consequent is false, then the conditional is false. So I think this makes sense if we think about it in connection to our sentence that we've already looked at here. If Jessica is strong, then Luke is strong. So that sentence, the whole thing is true if Jessica is strong and Luke is strong, right? In other words, it follows that if both Jessica and Luke are strong, that if Jessica is strong, then Luke is strong. You might be tempted to interpret a kind of causal connection here, but this isn't really like a causal relationship. It's not saying that Jessica's being strong makes Luke strong. Instead, it's just saying that if this condition holds, then this other one holds. And so we can see in the second row that, suppose Jessica is strong, but Luke isn't strong. Well, then the statement, if Jessica is strong, then Luke is strong, would be false, because we have here an instance where Jessica is strong, but it doesn't follow that Luke is strong. Okay, let's now turn to look at the other two rows of the conditional truth table. So consider this sentence. If you give me $1 million, then I will give you an A in the course. All right, now suppose that you give me $1 million and I give you an A in the course. Well, then this sentence follows the pattern, and it turns out to be true. Suppose you give me $1 million and I don't give you an A in the course, then I have lied in saying this. This sentence turns out to be false. But what if you don't give me $1 million? Well, in that case, it doesn't matter what happens. If I give you an A in the course after that, in other words, if the antecedent is false but the consequent is true, this sentence still remains true in the logical sense. So if you give me $1 million, then I will give you an A in the course is not given there's not a counterexample posed by that, by you're not giving me $1 million and still getting an A. Furthermore, if you don't give me $1 million and you don't get an A in the course, then this sentence is not proved to be false either. Right? So this sentence says that one way to get an A in the course is to give me $1 million. So if you give me $1 million, then you will get an A. But it doesn't say the only way to get an A in the course is to give me $1 million. So in both cases, this sentence turns out true if the antecedent is false. In other words, the antecedent being false does not present a counterexample to the truth of this sentence. In the same way, we are shown that the sentence is false when you do give me $1 million and I don't give you an A. But notice the difference here. If I had said, I will give you an A in this course only if you give me $1 million, that's much stronger. This is saying that the only way to get an A in the course is to give me $1 million. It's saying that giving me $1 million is required to get an A. And this means that any students who gets an A has given me $1 million. So if you do get an A, then you gave me $1 million. And this is best translated as if then. So how could you translate this into SL? What if you had to translate, again, this sentence, if I will give you an A in the course only if you give me $1 million? Well, the way this would be translated is that the consequent of this conditional is going to be give me $1 million. So this will say, if you get an A in the course, then you gave me $1 million. So only if is much different than if. If is going to identify an antecedent of our conditional, only if is always going to identify the consequent. Okay, let's turn to the biconditional now. So consider the following sentences. Jessica is strong, Luke is strong. Suppose we want to translate this into FOL. Well, this would be translated as, this symbol, J if and only if L, or J biconditional L, gets interpreted as Jessica is strong if and only if Luke is strong. So let's turn and practice with some of our these exercises, and see how to translate this symbol. So sentence 1 says, the figure on the board is a triangle only if it has exactly 3 sides. And so what's this going to get translated as? This will get translated as, again, so only if is going to identify our consequent of our conditional. So this gets translated as follows. And again, remember, a triangle is a triangle. Figure is a triangle is going to be interpreted as T. The figure has 3 sides. It's going to be interpreted as S. So we might write this as follows. So only if identifies our consequent. So we're going to say this sentence is symbolized by T. If T, then S. If it's a triangle, then it has 3 sides. Because only if, again, identifies the consequent of our conditional. So that's 25. 26, on the other hand, is going to be just the opposite. It's going to be interpreted as, so here, notice we have if instead of only if. So this is going to be interpreted as, the if is going to identify the antecedent of our conditional. So this one's just going to be flipped. It's going to say, if the thing has 3 sides, then
it is a triangle. If it's a three-sided figure, then it is a triangle. Now, what about 27? So this says the figure on the board is a triangle if and only if it has exactly three sides. So we could translate this as follows. The figure on the board is a triangle only if it has three sides, and the figure on the board has three sides. If the figure on the board has three sides, then it is a triangle. But we're actually given a separate way of representing this complex state, and that is through a biconditional. So we can use the biconditional to translate using the symbols we already have into the following. And so what this means is the figure on the board has three sides if and only if it's a triangle, or I guess the way it's actually written here. Doesn't really matter because the logical relationship goes both directions between these two, but this is going to be equivalent. If the figure is a triangle, the figure is a triangle if and only if it has three sides. So that is how we are going to symbolize using our biconditional symbol. Okay, let's go back to the PowerPoint.
Okay, so again, for each connective, the truth of the complex sentence depends on the truth or falsity of the component sentences. And here is how that works for biconditionals. So for a biconditional, the sentence is true. The biconditional sentence, phi if and only if psi, is true in any instance where the truth value of the atomic or the underlying sentences that make it up have the same truth value. So if it's true the figure on the board has three sides and it's true that it is a triangle, then the sentence, the figure on the board is a triangle if and only if it has three sides, is also true. If it's false that the figure on the board has three sides, it's also false that it's a triangle, then the sentence, if the figure on the board has three sides, if and only if it's a triangle, remains true as well. It doesn't provide any counterexample to that sentence. But if the figure on the board has three sides and isn't a triangle, then our biconditional sentence turns out false. It's not going to be the case that if it has three sides, if and only if it's a triangle, and vice versa. If the figure on the board, if the figure on the board is if it's false that the figure on the board is a triangle, but it does have three sides, then it's false that if the figure on the board has three sides, that the figure on the board has three sides, if and only if it's a triangle. Again, the important thing to remember is a biconditional sentence is true if and only if both of its conjuncts or both of its biconditional components have the same truth value. So a biconditional sentence is true only when the sentences that make it up have the same truth value. Okay, now let's try to put this all together and translate the following sentences. So we'll go back to the iPad and take a look at these.
So here are our sentences. S1 stands for you will get soup, and S2 stands for you will get salad. So you may want to pause here and practice what each of these mean yourself. And I will give you the answers in just a second after you unpause. Okay, so let's take a look at this. So you will get soup, and you will get salad. So our first sentence is going to be translated as, if you, I'm just going to shorten it to say you get soup. If you get soup, then it's not the case that you get salad. Our next sentence will be understood as you get soup if and only if, and this is a philosopher's method for writing in a shorter way, if and only if, IFF. You get soup if and only if you get salad. Our third sentence, remember, we're going to translate inside of the parentheses first. So we're going to get, you will get soup. If you will get soup, then you get salad. If you get soup, then you get salad. So what does the whole sentence say then? It says, if you get soup, then you get soup. Then if you get soup, you get salad. And our last sentence is going to tell us if, so that's our overall if-then statement. So we can write that in first. If, so that is this guy. If you get soup and you get salad, so we can say if you get soup and salad, and then we have the then that is also part of that conditional, which appears between the two parenthetical statements here. And then we say, then you get soup or salad. So if you get soup and salad, then you get soup or salad, which is clearly true and evidences the nature of the inclusive or. Okay, a weird English word that we have to practice with to translate into symbolic logic is the unless, the word unless, okay? So consider this sentence. Unless you wear a jacket, you will catch a cold. Well, what are the atomic sentences here? Well, one is you wear a jacket, and the other is you will catch a cold. So we'll symbolize these with J and D. And now moving towards symbolizing this in symbolic logic, we might say unless J, comma, D. So essentially what we're saying here, and we can see this from thinking about the sentence, is that there's a kind of consequential effect to not wearing a jacket, right? If you don't wear a jacket, it looks like, then you will catch a cold. So unless is going to symbolize the if it's not the case, then, if it's not the case, then operation, okay? So unless stands in for a if-then statement where the where the antecedent, the thing that comes before the horseshoe, is negated. So we will symbolize, unless you wear a jacket, you will catch a cold, as if it's not the case that you wear a jacket, then you will catch a cold. So we translate unless phi psi as if not phi, then psi, or to put it in symbolic logical form, negation phi conditional psi. And that's what's in the parentheses. Okay, that's it for lesson 5. See you at lesson 5B.